On this episode of Science Room starring Gabriel Suhm, we will be explaining electronegativity.
Hello class! Today we will be discussing intermolecular forces and what they mean in the science world. First up, we have to teach you about the octet rule. So, you may be wondering, what exactly is the octet rule? Well, it's actually very basic. The octet rule states that an atom will tend to bond with another atom if it gives it 8 valence electrons. Valence pretty much just means 8 on the outside shell. Why does it do that? Well, for that, we will come over here for an experiment. Leia, come here. This is my dog, and she feels more stable when she has food.
This is a perfect example of why atoms are attracted to atoms that will help them fill out their 8-electron shell. They just feel more stable, just like my dog when she has food.
So now you know about the octet rule, and it's time to learn about one more key principle, electronegativity. What is that? Well, it's the tendency to attract shared electrons. Pretty much this means that it's the tendency for an atom to want to connect with another atom. And they have different strengths. Some of them are really weak, and some of them are really strong. They really want to get that 8th electron on the valence shell. So there's actually a key to this. So when you look at the periodic table, so from the left side, electronegativity increases as you go to the right. And then from the bottom, it increases as you go to the top. This makes fluorine, which is located right up here, the most electronegative atom.
For those of you asking why the periodic table has such a trend, well, here's an answer for you.
The reason for this greater attraction is that the nuclei are closer to the electrons, which happens in smaller elements. Think about it. Like in cameras, when the pixel density is higher, the whole picture looks better. Pretty much, in better terms, when the pixels are closer together, they make better pictures at a higher resolution. That's the same for elements. When the nuclei are closer to the electrons in smaller elements, it creates a bigger attraction. That's why fluorine is the most electronegative element, and cesium is the least. Another aspect of electronegativity is bond polarity. This happens when a bond is offset, pretty much when one side of the molecule is a little bit more electronegative than the other. For example, if we take water, H2O. So we know oxygen is one of the most electronegative. Hydrogen is pretty electronegative, but not as. So when they bond, oxygen pulls in a little bit more of the hydrogen, creating an offset, which means that the bond is polar. So when you're calculating bond polarity, you usually subtract the electronegativity of one and the electronegativity of the other. And this gives you how polar the bond is. One type of bonding is ionic bonding. This is a very polar bond. Aren't you very polar? Huh. That's Leia, our science buddy. Ionic bonding is a very polar bond between atoms, which is a cation and an anion. We have an example right here of Li, lithium, and F, fluorine. As you can see, fluorine takes up all the electrons, creating an octet, the octet rule. Hello again. Aren't you happy? Alright, let's go. That's because, as we know, fluorine is the most electronegative of all the elements, whereas lithium is not. So fluorine takes its atoms all the way away. This creates an ionic bond. Another type of bonding is covalent bonding. This has 2 subcategories, nonpolar and polar. Both these are less strong than ionic bonds, which are very, very strong. So as you can tell from the names, a polar covalent bond is when the bond is very polar. Not quite ionic, but still stronger than nonpolar. Here we have the values. If the combined electronegativity is between 0.5 and 2.4, it's classified as polar. Here's our example, H2O. As you can see, O is much stronger than H, which creates an offset and gives H more electron share than than on the hydrogens. This actually uses, this is a secret, but this actually uses a special kind of hydrogen bonding, which is exclusive for between hydrogen, fluorine, nitrogen, and oxygen. The other kind, non-polar covalent, it's not as strong as a bond, but it also has less, it's more close to perfectly equal. This has a combined electronegativity of 0.5. Here our example is H and H, two hydrogens. The reason for this is all atoms combined with another atom will be perfectly polar, and perfectly non-polar, meaning they are perfectly equal. As you can see here, the electrons are shared perfectly and gives both of these 2. On here, this links back into the octet rule, where because oxygen bonds with the 2 H's, it gives it 8 electrons. The octet rule. The last topic we have to talk about today is VESPR, or valence electron shell pair repulsion. Pretty much, in simple terms, that is a process used to predict the geometry of molecules. It may sound difficult, but it's not that difficult. Pretty much, you can use symmetrical rules to tell if it's going to be non-polar or polar. Generally, symmetrical ones like this tetrahedral are non-polar, meaning they have an equal spread. You can also use these arrows, which you use with the electron pairs to tell whether it's going to be non-polar or polar. Pretty much here we have carbon dioxide, and because these arrows are pointing out, you know that it's a non-polar molecule. Whereas over here with H2O, these arrows are pointing in at the inner molecule, O, and that way you can tell that it's a polar molecule. This goes much more in depth, but I'm not here to teach that. That's for your science teacher. This has been your weekly episode of Science Room, brought to you by our workers. Ethan over there by the camera.
Hello.
And Leia, right here, our science dog. Come here, Leia. Up. There you go. Everybody say, bye, hypothesis.